Hi everyone, this is team number 7. Our project is DeepNCheap model search TF Carrot's contribution. Our mentor is Professor Chugg and Dr. Day. We are Zhibing Chen, Zhixuan He, and Tian Yizhang. I'm Zhibing Chen, and I will give a brief introduction of our project for you. First, thanks to AWS education program for providing us many queries for cloud computing. Today, we are going to follow these 4 sections. The first one is introduction. What is AutoML? Well, automated machine learning is that given a data set, the AutoML framework will try to find out a decent model and without any others help. And currently, there are many related work like AutoKeras and AutoPytorch. And for our project, DeepNCheap, this is a brand new AutoML framework proposed by Dr. Sourya Dey. And the core idea is using Bayesian optimization and grid search to search a certain model. And the process is a 3-stage search. As for the 3-stage search, regarding to this picture from the original paper, the first step is called architecture search. And the second one is for advanced architecture search. Finally, there is a training hyperparameter search. At each step, the framework search for the model architecture and for the training hyperparameters step by step. Finally, you will find out a good model. As for our contributions, at first we will reproduce previous work. Since the previous work is written in PyTorch interface, and we support this framework with TF.Keras interface. And then we do some innovation. We do standalone training split tests between TF.Keras and PyTorch. And we also add hyperparameter search on the activation functions. We also support for the regression problem and INN problem. Our code is available at our GitHub repository. And for the MLP and CNN, we first define a new model inheriting from TF.Keras model. We take the default network hyperparameters as a baseline and gradually refine the hyperparameters. And especially, we define a software structure which decouple these 2 different frameworks. No matter you use only TF.Keras or PyTorch, you can run our software correctly. Here is how we do grid search on activation functions. For example, we search over ReLU 10H and sigmoid function. Each time we apply the same ReLU function, the same activation function for every layer, and then we will find out which one performed the best on the validation set. And here come to the regression part. In the original paper, the objective function is defined as this way. And the performance part is defined as 1 minus best validation accuracy. But now for the regression problem, the accuracy is not available. So we can just evaluate our results by loss. So we can define it as a new way, best validation loss times a scale factor. This factor is made sure this term is between around 0 to 0.1. And here's 2 examples. The first one is a linear function. After we learn the model from the framework, we can converge within 3 epochs. And this is a more difficult dataset generated by ourselves to evaluate our method. And it take after we got the model from the framework, it can converge after 60 epochs. Here are the results on our standalone training speed test. For NLP, we use MNIST dataset. As shown in the result, using NumPy array is generally faster than using data loader. I think the reason might be because NumPy array loads the data into memory at the first time, while data loader loading data and training simultaneously. So using NumPy array is definitely faster than using data loader. For the CNN part, we use the Cypher10 dataset. And at this time, PyTorch is always faster than TF-Keras. And here's the results of our MLP classification. And the PyTorch is faster than TF-Keras as expected. Well, at this time, they perform similarly on the accuracy. Moreover, TF-Keras might a little better than PyTorch. And WC is a penalty term which penalty the complexity term. With the increase of WC, then the framework tend to learn a lighter network. Here are the results of our CNN classification. PyTorch is still faster than TF-Keras. While at this time, PyTorch performs slightly better than TF-Keras. And then with the increase of WC, the framework also tend to learn a lighter network. Here's our results on a MLP regression. PyTorch is also faster than TF-Keras. While at this time, the performance of TF-Keras is rather better than PyTorch because it's 10 to the minus 2, while the PyTorch, the loss is 10 to the minus 1.
Hi, my name is Chen Zhang, and my major task is to explore the RNN, and this is my steps to realize this function. And at first, I choose IMDb dataset to test our function, and this is some processing, and we have made many experiments, and these are some results. We can find that we don't need to add any MLP layers, and accuracy is just very similar, and we can save much time. And we compare the GRU and the LSTM, and we check whether the complexity penalty is useful for RNN. And we still have some future works. For example, we can add more hyperparameters to search, like dropout rates in RNN, and we can support more data size and support RNN PyTorch version.
Hi again, I'm Zibing Chen, and now I will give you a demo of how to run our code. At first, you should git clone our Git repository to your local machine, and then type python main.py --network. And here you can choose NLP, CNN, or INN. And now I will give you a demo of NLP and choose your data folder. This is the folder where you store your NumPy array. And I choose MNIST. And I set a validation speed as 0. And in this data set, the input size is 784, and output is 10 class probabilities. And this is the WC, which is the complexity penalty term. And number equals as 10. And now we can use DL framework to choose PyTorch or TF.Keras. And we can choose the problem type between regression or classification. Now it's work. Thank you.